So hydrates is the topic for today. And it's going to be a way that we're going to be able to actually find something like an empirical formula, because to actually do a decomposition or a combination reaction is usually pretty messy, because you got to deal with at least one of the chemicals really reactive. So you end up with, either I have to give you something that will hurt you, or you end up with something that will hurt you. So you can't really do a lot of decomposition reactions in class or combination, because one side or the other has to be really reactive. So we're going to be able to do part of an empirical formula by using hydrates. Okay. When you see the word hydrate, though, what do you think of? Water. Yeah, and that's what it means here. It means water. Okay. So a hydrate is an ionic compound that, when it makes its crystal structure, it traps water along inside its crystal. That as those atoms go together to make the pattern includes some water molecules that are just laying there. So the ionic crystal has been hydrated. It's got some water added to it. So it's not. This is not liquid water. This is as a solid. Water is part of that solid. It's hanging on to some component of the ionic thing. Okay. And there's got to be a best structure. There's got to be a best way to put them together. And if there's a best way to put them together, they're always going to be that way. So you're always going to have the same number of water molecules for every ionic compound. It's going to have the same number of water molecules. It's not going to be some random number. That chemical gets this much water every time. So when we're talking about that chemical, when I want to go buy it in the store, I have to mention the water, because the water is going to affect the weight. Okay? So in our name and in our formula, we've got to include that water. So the number of water molecules shows up in the formula at the end after a dot. So if you had 3 extra water molecules, you would put dot 3H2O. I don't know if you've ever seen they were actually fairly popular when I was a kid, but now they got electronics. It was a color thing that would change between pink and blue, whether it would rain, whether it was supposed to rain or not. Pink if it was supposed to rain, blue if it wasn't. Okay? And it was actually about the water adding on to cobalt and changing the charge on the cobalt. Because when you buy cobalt chloride, you usually buy this, COCl2 dot 6H2O. If it doesn't have 6 H2Os, it changes colors, because it can make a second one with fewer waters. Okay. But we need to say that out loud. Well, the first half is not hard. Cobalt needs Roman numerals. Cl is 1 minus, so it's cobalt 2. Chloride. Now I just have to say the 6 waters. So what I do, in the name we use the prefix for the number of water molecules. So this has 6 water molecules. So the prefix that means 6 is, 6 was hexa, like a hexagon. Okay. So my cobalt 2 chloride, I need to say 6 waters. So I go cobalt 2 chloride, hexa, hydrate. 6 waters. That's pretty straightforward, isn't it? Hexahydrate. So, a new set of naming and writing formulas rules. All you got to do is put a dot or put how many waters there are, right? So it shouldn't be too bad. So name this chemical. Well, the first part, barium. Barium's a metal. It's in group 2A, so it doesn't need Roman numerals. Cl is chlorine, but it's acting as a negative ion, so I change this to chloride. And then I have to say two waters. Dihydrate. Ta-da. Earth-shattering, right? See how much pent-up energy they have. Okay, magnesium doesn't need Roman numerals. OH was hydroxide. And then 5 waters. 5 was pent and pentahydrate. Put the A back in there, pentahydrate. Sorry. Extra super tough. Got to be able to go the other way. Sodium carbonate decahydrate. Well, sodium is Na. It's a metal, so I have to worry about the fact that it's +1. Carbonate, ATE, polyatomic ion. CO3 with a 2- charge. 1 plus and 2 minus doesn't add up to 0, so it's got to be Na2CO3. So that's sodium carbonate. Now we need decahydrate. Deca. 10. Just almost a decade. 10H2O. Dot 10H2O. Extra tough? Let's try calcium sulfate dihydrate. My favorite hydrate. I'll explain why in a minute. Well, calcium is Ca, it's 2 plus. Sulfate, SO4, 2 minus. Adds up to 0. It's calcium sulfate. Dihydrate. Dot 2H2O. My favorite. Okay, so this, when you dig it out of the ground, is called gypsum. Like Gypsum Canyon off the 91. Gypsum, it's a white thing, but sometimes known as alabaster. Okay. It's the stuff in drywall. Okay. Why it's my favorite? Because when I worked in a quarry, I worked in a gypsum quarry. Actually, I didn't work in the quarry end, I worked at the mill end, where they ground it up. Okay. So I learned a lot about gypsum. Okay. And it goes in everything. So I'll talk about why we have, what we can use it for, but the other thing we use this for is not just drywall, we use it for plaster. Take that white muddy stuff and then it dries on. That's because it's becoming a hydrate. Okay, so calcium sulfate's a big component of cement. Notice cement starts off with everything flowing, but you turn it into a solid. Why does that work? It's about hydrates. Okay, so when I worked at the quarry, my first year I worked on the line trying to load boats with rock. But the next year I worked in the quality control lab, and we had to check to see how pure our rock was, because we guaranteed 93% purity. Okay? And the way we checked our purity is trying to see how much water there was I can get to come out of that rock. Because if I heat up calcium sulfate dihydrate, I can get that water to leave. Does that make sense? Okay. It's going to tear apart the crystal. So I'm going to start off with crystals, and they're going to fall apart. It's not going to be stuck together anymore. But I can draw that water off, because that water is part of that crystal. So when I get rid of the water, the crystal falls apart. Okay. So I want percent water. So percent water is going to be the grams of water over the total grams times 100%. Anybody got any problem with that? That's right. So, does it matter how much calcium sulfate I have? Is that going to change the percent water in the calcium sulfate? I can pick any amount. Okay? Because it's percent, I'm going to pick an amount that makes my life easy. I'm going to pick 100 grams. Why would I pick 100 grams? Well, because if I had 100 grams, nah, I don't want 100 grams. It'd be too hard. I'd have to do all this stuff about conversion factors. How about I pick 1 mole? Can you figure out how much the calcium sulfate dihydrate would weigh if you had a mole of it? And how would you do that? Well, you'd add up the calcium sulfate and the water, right? So you'd have to figure out the water along the way. So just from the formula, I can do this. So if I assume 1 mole, then I've got 2 moles of water. If I got 1 mole of CaSO4, I got 2 moles of water. That too. Right? So, and a mole of water is 16.00 plus 2.02, so that's 18.02 grams. So 18.02 grams of water is 1 mole of water. 18.02 grams. Oops, that's not what I want. I want that multiplied, which is 36.04 grams. So in 1 mole, I'd have 36.04 grams of water. I'd have calcium. I'd have 1 calcium. So that's 40.08 grams. I'd have 1 sulfur at 32.07 grams. I'd have 4 oxygens, and by now, hopefully, you're used to writing 64 for that, rather than taking the time to multiply 16 times 4 over and over again. But what I usually do, I usually multiply, because the reason why you don't want to do 16 times 4, it tells you my last digit's right. Okay. And that adds up to 136.15. So that's a CaSO4. But I also have 36.04 grams of water. Don't forget that water's still there. 172.19. So 36.04 divided by 172.19 equals times 100, 20.93% water. So here's how we check to see how pure our gypsum was when I was in the quality lab. Okay, we had samplers that would take rocks out at random from different places in the quarry. Then I'd bring those rocks in and I'd grind them up into a powder. Then I'd take that powder and I'd put it into an oven, but not a hot oven at about 140 degrees Fahrenheit. And I put a sample in there, I weigh it before I put it in there, and I put a sample in there and weigh it when it comes out. Because there's going to be some water that's not in the crystal. I mean, we dig the rock out of the ground, it rains on top of that pile. They don't dry the pile off before they dig it up and throw it in the crusher. So there's just some extra water. So I want to make sure my calcium sulfate is dry and that the only water left is the water in the crystal. So we take and put it in the oven, let it dry for a couple hours. Okay? Then after it had dried for a couple hours, then we take and put it into a high temperature oven. In the high temperature oven, all the water would come out. And the closer we got to 20.93%, the more pure our rock was. So we can tell how pure the rock was by how much water came out, because the only place the water should come out is from that crystal. So that's how we check to see how pure the rock was. We just heated it, weighed it before and weighed it after. So if I give you a formula, you can figure out the percent water. Guess what that means? If I give you the percent water, you can figure out the formula. And until you get to quantum mechanics, everything's reversible. I mean, that's what your math teacher does, right? They teach it to you one way and then turn it around and make it work the other way. Because math is reversible. Okay, so somebody took some zinc nitrate, weighed it before, heated it up, weighed it after, and it lost almost half of its weight, 43.3%. How many water molecules are in zinc nitrate? Well, that number is a number of moles, right? So if I take the moles of water and divide it by the moles of zinc nitrate, zinc's always 2 plus, that will tell me how many waters I have for every zinc nitrate, which is the number I'm looking for. Because I know it's going to be Zn NO3 2 dot X H2O. And we're trying to figure that out. So if I take the moles of water and divide it by the moles of this, that'll tell me how many of those I have. Seem reasonable? Okay. So how can I get those numbers? Well, that 43.3%, does it matter how much I have? If I have a ton of it, 43.3% is still going to be water. If I have an ounce of it, 43.3% is going to be water. So I can pick any amount and it's still going to be 43.3%. I am going to pick 100 grams. Why would I pick 100 grams? Because then I have 43.3 grams of water and 56.7 grams of zinc nitrate. Because anything that's not water has got to be zinc nitrate. Oh, got that wrong. The 3's inside, there's a 2 outside. I have grams. I don't want the grams of those. I want moles of those. If we just knew how to turn something in grams into moles. We may have done that once or twice. Want to get grams of H2O, change that to moles of H2O. And 1 mole is 2 H's is 2.02, 1 O is 16, so that's 18.02. So that I have 43.3 divided by 18.02. I have 2.40 moles of water. And my zinc nitrate, need to get rid of grams of zinc nitrate. Change that into moles of zinc nitrate. And zinc nitrate, zinc is 65.38. 2 N's, so plus 28.02. Plus 6 O's, that's 96, equals 189.40 and 56.7 divided by that gets me 0.299 moles of zinc nitrate. So my moles of H2O was 2.40. My moles of zinc nitrate was 0.299, which you can tell 0.299 is pretty close to 0.3. And 2.4 divided by 0.3 is the same as 24 divided by 3, which is 8. So, 8. That 8 we figured out was how many water molecules I have to be. So that's what you're going to do tomorrow. You're going to heat up a hydrate. Weigh it before, weigh it after, figure out how much water it lost, so you can figure out how many water molecules there were. Okay, to do that, you're going to have to heat it up. And those hot plates we said got hot, but not hot enough. So tomorrow, we're going to have to use Bunsen burners. Okay, and we used them once last semester for the flame test, but we haven't used them since. And when I gave for you the flame test, they were all adjusted. They will not be adjusted tomorrow. So we have to teach you how a Bunsen burner works and how to adjust it. Okay. Hey, it is about air and fuel. That's an important concept. Okay. So using a Bunsen burner. Okay, so first, let's look at the parts of the Bunsen burner. No, it's methane. No, there are going to be some notes, but you just need to understand the parts. Okay, so here's the Bunsen burner. Come on, you're supposed to be straight up and down. There we go. There's a Bunsen burner. And you'll notice that the top spins. And that as the top spins, there's an opening right here that opens up. And if I spin it the other way, it closes down. Okay, but that's not the only movable part. On the bottom, there's a knob that turns as well. Okay, so we got two knobs to adjust because to have a fire takes two things: fuel and oxygen. So these two knobs let us adjust those two different things. Okay, so first you're going to have to hook it onto the hose. Push it on there tight so it's not going to slip off. Make sure it's hooked on this side. So here's a Bunsen burner. Okay, to turn on the gas. Okay. To turn on the gas, if you look at the valves, sideways is off. Straight out is on. So this one's off. Now it's on. Now it's off. On. Off. Okay, and that's the only way we want to use it. We want to turn it either all the way sideways or all the way straight down. We don't want to put it halfway. It's either on or off. We can, because we'll adjust, because that's hard to adjust. It's easy to adjust at the other end of the hose. Okay, so here's notes. You turn on the gas by turning the valve so it points down the hose. If it's pointing at the hose, there's gas on. If it's not pointing at the hose, there's no gas on. So it's called a gate valve, the valve in there, because it's like a gate. When the gate is sideways, it's closed, and when you spin the handle, it opens up. So it's a gate valve. So what's hooked on underneath that handle is a piece of metal the same shape, same direction. And when you spin the handle, it turns pointing down the pipe so that gas can go on either side of it. But when you spin it all the way, it's flat again, and the gas can't go around it. Okay? So we sense how the gate valve works? Okay. Hey, so sideways is off. Okay, so we need to adjust the fuel and the air. Okay, first I want to show you why you want to adjust the air. Okay, so I'm going to turn this on. Okay, this is a poorly adjusted Bunsen burner. Okay, why do we need to adjust the air? Because that flame is yellow. There's two problems with the flame that's yellow. Problem number one, it's not very hot. Problem number two, can everybody see a problem with this? There's a problem with this, right? So the reason why it's yellow is because it's not getting a good mix of gas and air. The gas and air don't get a chance to mix till it's all the way up there because where's my mouse? There it is. Don't look at me. Okay. Because this valve right here is closed all the way. But if I open it up, air can start getting in. Okay? So I want to adjust the air. Okay? So I adjust the air by turning the whole top. And as I turn that whole top, you'll notice the yellow goes away and you get blue. Okay, and can you hear the sound change? Can you hear the air coming in? Okay, it's still not adjusted right. So, Finn, can I get you to shut off the lights? Okay. Go ahead and turn them all, both off. Okay, everybody see that blue flame? Okay, that blue flame is hot, but it's not as hot as it could be. And it's not that controlled. I can still get it to move around with my hand. Okay, but if I let in more air, did you hear how the air picked up as I opened it up? Okay, and can you see that there are now actually two colors of flame? There's a dark outside blue and a light inside blue. Okay, and the dark outside blue hasn't changed temperature, but the inside blue that is hotter, and the hottest spot is the tip of the inside blue. Okay, so the tip of the inside blue is the hottest spot. That's what you want to have heating your stuff. Okay, so you want to adjust the flame so that the tip of the inside blue is right at the bottom of what you're heating. Okay, well, the problem is I don't need to be heating stuff this far above a Bunsen burner. My flame's too tall as well. Okay, to adjust the gas, the bottom. The bottom is a valve, okay, that adjusts the gas. So the top adjusts the air. Notice how I cover up the holes, I get my yellow flame back. No, it's not, I'm fine. I've done this before. Notice my tie's in the sink. Okay, so this is what you want your flame to look like tomorrow. See how it's got two colors? It only needs to be a couple inches tall because you don't want to raise the thing you're heating way up in the air. Right? Seem reasonable? Okay. And if you look, your stove is already adjusted this way. If you've got a gas stove, that when you spill stuff on it, it turns yellow because that cools it off too much. Okay? All right, then can I get the lights back on? Okay, so now we can take notes on all this. Okay, so we adjusted the air by turning the whole top. The whole top spins. Don't spin it all the way off. Okay? And what is that going to affect? The air to fuel ratio, what are you going to see because of that? You're going to see different flame colors. It goes from yellow to dark blue to light blue. So a cool flame, less than 500 is one that's blue. A hot flame has two blues, one light, one dark, and the tip of that light inner blue is hot enough to melt glass. Okay, so it gets hot. This is not run your finger through it like a candle on a birthday cake. Because then you just make an ash of yourself. Okay, you adjust the gas flow by turning the knob on the bottom. Okay, and what that knob on the bottom is tied to, it's called a needle valve. Because at the end of the thing you're turning is a needle, a cone-shaped needle. And it's going into a socket that is also cone-shaped, but in reverse. So that as you tighten it, the space between the cone shapes get smaller and smaller until they seal up against each other. So if you're going upward, you're putting that needle into the cup. If you back it out, you're pulling that needle out of the cup. That's why it's called a needle valve. Okay? So that's why you're turning it versus unscrewing the opening. Okay? And why would you want to adjust the flame? What are you adjusting if you adjust the bottom one? What's going to change about the flame? Height. Yeah, flame height. Okay? So we'll be using these to heat stuff. You see I've got most of the things set up already. Getting ready for tomorrow. Okay? So, tell me, what part of the Bunsen burner do we use to adjust the gas? Is it A, the valve on the table next to the hose? B, is it the top of the Bunsen burner? C, the valve on the bottom of the Bunsen burner? Or D, you don't need to adjust it, it's already set up? Hey, which one? What am I trying to adjust? Gas. Where does the gas come in at? Here. What does it run into? There. It runs into that valve, so it's probably the one that controls the gas. So the answer was C, valve on the bottom. And if you think about how they're connected, it makes sense, right? What part of the Bunsen burner do we use to adjust the air? Is it A, the valve on the lab table next to the hose? B, the top of the Bunsen burner? C, the valve on the bottom of the Bunsen burner? Or D, you don't need to adjust it, it's already done? Okay, the first time you used Bunsen burner, the answer to these first two questions was D, but not now. Okay, and of course the answer is something we've seen before. Okay, so yes. Because learning how to adjust the flame is an important skill. Because we're going to have times where we're going to need to adjust the flame, heat it at a low temperature for a while, and then heat it up later. Fact is, the instructions tomorrow are going to tell you to heat it for a low temperature for a while, and then increase the flame temperature. Okay, your Bunsen burner is making a yellow flame. What do you do? A, leave it alone. Flames are supposed to be yellow. B, turn the valve on the bottom to adjust the air. C, turn the valve on the bottom to adjust the gas. D, turn the top to adjust the air. E, turn the top to adjust the gas. If you see a yellow flame tomorrow, what should you do? D, turn the top to adjust the air. It's yellow because it doesn't have enough air. The part that's nearest the air, you can see where the air comes in. Make it a bigger hole for the air to come in. Okay. The next one, you can fail the class if you answer incorrectly. Your Bunsen burner has a flame that is too big. What do you do? A, leave it alone. Flames can't be too big. B, turn the valve on the bottom to adjust the air. B, turn the valve on the bottom to adjust the gas. C, turn the top to adjust the air. E, turn the top to adjust the gas. And everybody can recognize which answer gets you dropped from the class. Okay, so it's A is the one you don't answer. The correct answer is I've got a big flame. I need less gas. I need less fuel. So the fuel changes the size of the flame. The air changes the temperature of it. Okay, and then on your homework, this is what it looks like. Yeah, ammonium ferrocyanide. Ferro for iron. That's why iron's Fe. Ammonium ferrocyanide. Oh yeah. They're all phonetic, so it's okay. No. Just here. Because this is on off. We want to use that as on off. Question, Logan? 45. How many atoms of each element are contained in a singular formula unit of this? HCH2O. Oh, CHO2, sorry, CHO2. It says how many atoms of each element are in a single formula unit of iron 3 formate. But then the second half, what percentage by mass? So the answer to so the first answer is 1 iron atom. So there. so can you follow it from there? 1 iron atom.
Yes.
You always get a little messed up in the H's, but man. So need to stop that.